This is a short overview over the relativistic kinematics of the three-body decay. Let A be a particle that decays into three particles B, C, and D. We want to examine the energy of one of the decay products in the rest frame of particle A. To do that, we will use the following three statements. Firstly, the energy squared of a particle is equal to its momentum squared plus its mass squared. This is the so-called energy-momentum relation. Secondly, the form momentum Q is conserved. This combines the conservation of energy and the conservation of free momentum. Thirdly, we know that the inner product of two 4 vectors is invariant under Lorentz transformations. For brevity, we will use Gaussian units where the speed of light is set to unity. If you want to use SI units, you just need to rewrite statements 1 and 2 as follows. We will start with the conservation of form momentum. The form momentum of particle A must be equal to the sum of the three form momenta of the decay products. We can split this equation into two. Equation 1 stating the conservation of energy and equation 2 stating the conservation of free momentum. Since we are in the rest frame of particle A, the free momentum of particle A is 0, and therefore the energy of particle A is just given by its mass ma. To clean up our two equations, we will write energy CD for the sum of energy C and energy D, and momentum CD for the sum of momentum C and momentum D. Doing so, we are treating particles C and D as one particle traveling with a momentum CD. In the next step, we use the energy-momentum relation to rewrite energy CD as the square root of the momentum CD squared plus the mass CD squared. We can now plug equation 2.4 into equation 1.4. Bringing energy EB on the other side and then squaring both sides leads us to equation 1.7. We now use the energy-momentum relation a second time to replace the energy B squared with the momentum B squared plus the mass B squared. Solving for energy EB then gives us equation 1.9. This looks exactly like the equation we get for the two-particle decay. The difference now is that we don't know the value of mcd squared yet. Since we started our calculations with two equations but three unknown variables, we cannot expect to get a single unique solution. An underdetermined system like this can either have no solution or infinitely many solutions. Because no solution would mean that the decay wasn't possible in the first place, we will look at the case with infinitely many solutions. The masses of particle A and particle B that appear in equation 1.9 are both constants. Therefore, mass mcd must be able to take on infinitely many values. A mass that can have infinitely many values could sound a bit odd at first. I will try to give an intuitive explanation for this at the end of this video. First, we will try to find out the range of possible values for energy EB. The minimum energy of particle B is just given by its mass mb. In this case, particle B has no free momentum in the rest frame of particle A. By looking at equation 1.9, we see that EB takes on its maximum when mcd is at its minimum. To find out the minimum possible value of mass mcd, we go back to equation 1.6. We are still in the rest frame of particle A. Therefore, the mass ma is nothing else but the energy of particle A, Ea, and the free momentum of particle A is 0. Therefore, we can rewrite this equation as the form momentum B minus the form momentum A squared. Because of the conservation of form momentum, this is the same as form momentum C plus form momentum D and then squared. We now use statement 3 from the beginning. The inner product of two 4 vectors is Lorentz invariant. Therefore, we can choose every reference frame we like without changing the value of mcd. The rest frame of the center of mass of the two particles C and D is a clever choice. In this reference frame, the sum of the three momenta of both particles is 0. Consequently, the sum of the two four momenta squared is equal to the sum of the two energies squared. In the rest frame of MCD, the two masses MC and MD are still constants. The squares of the two momenta PC and PD are greater than or equal to 0. Therefore, MCD squared is just greater or equal to MC plus MD and then squared. This gives us the following range of values for the energy of particle B. Let's look at what happens in the cases of the two extremes. If the energy of particle B is just given by its mass mb, particle B stays in the exact same spot as particle A before the decay. Particles C and D travel in opposite directions, carrying a lot of momentum. In fact, the whole energy difference between the mass Ma and Mb is now stored in the mass mcd. It's now at its maximum. In the case of maximum energy of particle B, particles C and D travel in the same direction, which is opposite to the direction of particle B. When particles C and D travel at the exact same velocity, they don't have any momentum in the rest frame of their center of mass. mcd is now just given by mc plus md. One can now see that the quantity mcd is the sum of the two masses mc and md plus the energy that is stored in their motion against each other.